Hi, everybody. Welcome to the last talk in our series here. It's a real pleasure to introduce Baihan Lin to come and tell us about his work. Baihan has a really unusual background, and it comes from lots of different places, and I think comes together in a really interesting way. He's a neuroscientist. He did his PhD in neuroscience from Columbia, and he's actually a neuroscientist working at Columbia now. He did his master's in applied math at the University of Washington. And he's also done a master's in visualization at Parsons, or at least he's finishing it up. So he's, got background from lots of interesting places. We had a great, exciting chat this morning. He is working also, in addition to working at Columbia, he's got a position doing AI and HCI at the T.J. Watson Research Center for IBM in New York. And he's worked at many of the world's major IT companies and major players, doing various things with them over the years. So he's connected in industry as well as in academia. And I think comes to AI from a few really interesting places. So Baihan, take it away.
Okay, good afternoon, everyone. And thank you, Joe, for a nice introduction. And also thank you all for joining today, either in person or virtually, where most people are lately. So my name is Baihan Lin, and I'm from Columbia University and IBM T.J. Watson Research Center. I'm super excited to talk with you today about a topic which is near and dear to my heart, which is the intersection between neuroscience and artificial intelligence. So before I dive into the exciting topic of neuroscience-inspired AI and beyond, which is the topic of today, I want to start by saying anecdotes, which might get us all thinking. Right, so have you ever wondered what would happen when a neuroscientist and computer scientist walk into a bar? Well, the neuroscientist might say that, well, I love studying the brain. It is the most fascinating and complex organs in the human body. And the computer scientist might say, well, I also love studying the brain. It is the most complex and fascinating computer in the world. So although it might be like a corny joke, which is not very funny, but it actually touches the heart of a very important question that we're all trying to grappling for today, which is that how can we build intelligent machines which can truly understand the complexity of human cognition and behaviors? So before I dive into the topics, I would like to take a moment to thank the amazing teams of researchers and collaborators I'm fortunate enough to work on all those exciting topics. Their contribution to my studies and research have been invaluable, and I wouldn't have obtained all those results without their guidance and help. And also, I would like to thank to all my collaborators from Columbia, IBM, Miller Institute, Microsoft, Google, Mount Sinai, University of Washington, as well as Parsons School of Design. Okay, and also everyone else who has supported me along my ways. All right. So here is our agenda for today. So my research so far has been building intelligent agents as digital twins of complex biological and cognitive systems. So my past research has been mostly in healthcare domain, but I also care about other social good problems. So I will be starting from why we are doing this, and then so what do I mean by neuroscience inspiration, what I'm trying to build, and also a few examples on how I do it, and also envisioning the next steps. So I want to first mention this concept of digital twins. So digital twins actually arises, if you are not familiar, arises from the industry of manufacturing and aerospace engineering. So basically, they are virtual replica of a physical entity, like an object or process or a system. The useful thing about digital twins instead of like a traditional machine learning model is that we could be building a mechanistic or personalized representation of a digital model that we can simulate and optimize the process. And also we can also do interventions in simulations when we cannot really do the intervention on the actual object. So for instance, if the space shuttle is in the sky, you cannot just open it. And if we're doing a digital twins of a human patient in the healthcare domain, you also cannot just cut open someone. But it'd be nice to have digital models where you can simulate all the response for patient outcome. So here we go. extend this concept one step further into how do we build digital twins of our minds, which is itself also a pretty abstract concept by assumption. So how do we create a mind machine? So if we consider from the researcher's point of view, we'll be collecting a bunch of data collecting from potentially all different kinds of sensors that we have available. Many can be directly measuring your neuronal signals and all those kind. Some might be more low fidelity, like you're just based on speech or transcripts, and even like the imaging or genetic data can be very helpful. And also we'll be building some sort of models, which tends to some machine learning, deep learning model. You can also do more learning frameworks like reinforcement learning agents and other dynamic system. And then afterward, we will have some predictions, which are personalized and hopefully do future prediction and can be generalizable to new scenarios and even can inform us on interventional outcomes. So I would consider the first part, the data. Not only we are collecting those noisy and messy data that is not directly measured or directly measured, we can also learn from the neuroscience that we already have, and we treat AI in this context as a mind emulator, and we put the healthcare as part of our prediction domain. So that is interesting because as we can see now, the AI has been very useful to analyze neuroscience problem, especially when currently all the subfield of neuroscience are migrating from the hypothesis-driven studies to data-driven studies for all those like single-cell recording, high resolution, high throughput, and also individualized analysis, brain-wide association studies. So AI has been powerful to power neuroscience research, which is a known fact now in the neuroscience community. And also in the healthcare domain, there are people here also in MIT and beyond, very amazing research group working on how AI can help with healthcare domain. But I would like to argue in this talk that the neuroscience literature, neuroscience research is actually giving us some concepts of how to build a universal algorithm. So it can offer us universality, while the healthcare part can offer us individuality because it focuses on the variance or the extreme points inside entire spectrum of how humans would behave or think. So if we want to build in the future, like a generalist AI algorithm, we could be learning from the architecture and learning rules from neuroscience and also map those AI agents as a spectrum instead of like just like a one model fits all. So on the one side, we have mechanistic model, and on the other side, we have more context, it offers more context. So hopefully we could be building AI algorithm that has some sort of compositional generalization. So when we are thinking about building human-like AI, it is a controversy topic nowadays because I have to change my slides 3 times because of all the new developments going on lately. But anyhow, one point is that we now see large language models and generative AI model to be highly adaptive and also effective in all kinds of tasks. And some of them even exist as sparkles of AGI, which is some cognitive properties that is evaluated with cognitive method. However, this can also be like a dangerous path where some of them we don't want to anthropomorphizing them, since if we treat them as real AI, human-like AI, they don't actually care about our users per se, and also their empathy might be just fake empathy that learns from the statistical relationship. So it brings us to critical question. So first is, do we need AI to be more human-like? I believe this answer is pretty straightforward. It's a sounding yes, because we would want AI to be understanding the complexity of human beings, and they can understand our feelings and also understand why we're doing something. But also on the other hand, do we really want those AI to be more human-like? And this would be a more shaky questions, because say if we want to make them more human-like, some properties would be emotions or bias or other cognitive factors. On the one side, having those properties baked into our human-like AI, it can help us understand and reason about those properties so that they can do better things for the society, like curing disease or supporting mental health. But also, do we really want AI agent to make decisions based on emotions or bias that is innate in human beings that we might not want them, right? So I really like this definition by a book that I recently read. It is The Human Compatible by Stuart Russell. So they mentioned this concept on how machines or intelligence can be defined to be the extent that their actions are expected to achieve their objectives. But on the other hand, maybe what we are caring more is that whether the machine is beneficial. So in this case, we'll be changing this objective function to be that how can they change their actions so that they're expected to achieve our objectives. So in order to do that, we would need AI to be understanding what we actually care about, what our priorities are, and how we are feeling about different aspects. So with that being said, so let me dive into how we can make those make human AI a reality given the neuroscience inspiration. So I'm still treating the definition of the digital twins literally here to exemplify the scales of neuroscience inspiration to create mind-machine. This is similar to in the manufacturing business where we have a digital thread, meaning that different components, meaning how you can build a mind machine. How can you create a mind machine in a particular levels? On the one side, we have genes or very, very basic levels on, say, how your genes is encoded to produce some sort of proteins, and also on the molecular aspect, and also how can you build different synapses? How do your neurons communicate with one another? All the way towards network systems, behaviors, and even personalities would mean that we're thinking on the human level, right, as human beings, and also in the society level, how are different questions are understanding the neuroscience aspect. So I'm fortunate to work on several streams, on several digital threads of this line of work. Some are basically from neuronal firing pattern, how can we learn from it? And some are more on how can we learn from existing connectivities, like connectomes, and can we build better neural networks upon them? And also we can have attention mechanisms or in the network level, or how the agent is learning through reinforcement learning, and also how to learn from different personalities of those AI algorithms. So I want to pinpoint this towards what people are currently understanding for the neural networks, right? If you map it towards the Mars 3 levels, the implementation levels are more in the neuronal aspects. Algorithm would be more how the networks is construct and communicate with one another. And also the computation would be measured either in the behavior domain or the functional domains. And this application has been shown to have a lot of applications such as mental health, question answering, computer vision, some NLP tasks, and playing, even control the drones or process satellite images or inspect manufacturing scenes or seismic detection. And there is another scale here, which is the spatial and temporal scales. We also see that when we are characterizing this neuroscience process, many neuroscientists are also studying how, say, the evolution takes a part in shaping your neural circuitry or molecular configurations or genetic configurations. And also the development is another process that is very important. As we human beings, our brains is progressing over the years by learning through different experience. And also, even the network level, you could be emerging different subnetworks at different levels. Some are modular, some are more connected. And we could also think about how our behaviors are adapting towards certain scenarios, either in a short-term timescale or a longer timescale. So I want to point out that most deep learning models here still have a distance between our neuronal systems, right? So one particular property would be that many times our brain can do few shot learning, while the neural networks still requires, many of them still requires a large amount of data. And also our brains are more resilient to small changes to the input, and it is robust or adaptive to internal changes. And also, we could be growing our brain from a single embryo cell. So that is an amazing thing where when we are building our neural net itself, it has to be hand-coded. So we have to build, although there are neural architecture search algorithms, but still many of the network engineering is critical. And also, one important thing is that our brain only runs on very low resources. It only takes 20 watts of power, while many of the neural net requires massive power during training and testing. So how are they so efficient? And also, can we balance the stability and plasticities? So I will be given 3 small examples of creating neuroscience-inspired mind machines. So one is about attention mechanism. How can we learn from external and internal attention? And the second one is about reinforcement learning, how small tweaks on the reinforcement learning framework can give us better characterization of neuropsychiatric disorders. And also, lastly, I want to mention the language as a window to the mind and the gateway for intervention. So this is also connecting to our popular topics nowadays, like large language models and stuff. So first thing, attention mechanism. So attention in neuroscience, it is studied in different components. Anatomically, they are actually separate units from decision-making units. And it has some features like saliency and all those type. And also it has limited resources. And one interesting thing is that attention can be viewed as it is connected towards our decision-making process. It not only constrains and also biases the reinforcement learning process of the brain, and also the reinforcement learning in turn actually shifts the focus of the attention. So basically, it is not only a regulator of our sensory representation, which is quite important if you are building new interface, like some realities, because realities are based upon those sensory input. And also attention can be also treated as an effect of interpreting sensory or other data. So people understand this in 2 components. One is a bottom-up approach, meaning that those are passive attention. So no matter what happens, this saliency or attention would always arise through the learning process. And also a top-down, where you have something and you want to do an active attention given the context. So we model it as a decision choice made internally, driven by the word. So here's an example of, say, we are seeing ourselves like an agent. So here, obviously, the agent is kind of like a small agent inside your brain that is doing a decision to actually see where you should see, where you should look at, right? So on the left, we have a feature selection process, which is an external attention. So in this case, it can be modeled with a contextual attentive bandit as a simplicity. And in the downstream, we have internal attention, meaning that, say, if you have different brain region, or in this case, it is a neural network with many different modules. And you have agent, in this case, is some reinforcement learning agent, to pick a particular embedding or a group of neurons to as its representer, as its embedding to formulate downstream activations. And then they have a hierarchical process where you have different levels of embedding. So in a sense that we are seeing not only the embedding selection process, but also kind of like routing. How are information routed across different components of the brains? And then the brains can also update those embeddings just based on the specific context that actually yields the entire routing. So we can apply attention to both the external inputs and internal models for that. And it has been outperforming many benchmarking in online learning scenarios. I would also like to point out another concept called attention-driven award. As we mentioned that attention can also regulate the reinforcement learning itself. So what do we wish to attention to capture? So that will be connecting to economics and studies of utility, how we are perceiving our reward. How is there any reward biases when we are treating them? And also the reward objectives can be both the performance and some attention-driven criteria. Okay. I would also like to mention another passive attention. So this is a regularity-driven attention. And this comes from the principle of neuroscience, where traditionally people think that, Bayesian can be explaining all the perception process. You have assumptions, which is the more probable a certain thing is, the higher the firing rate. But actually it is so there has been a contradiction to that, which is when our brain sees the novel objects, they actually fire even more so. So that would mean that the traditional Bayesian assumption is incorrect. But another assumption, which is an information theoretical point of view, would be more interesting. Meaning, if your object is more irregular, it will be having more weights upon them. So the neurons are firing even more. So this also connects with very ancient concepts, I think, in 1980s or 1990s by Jeffrey Hinton and Rich Zimmer about this implicit space of neural net, right? So in this case, it is kind of like the minimized implicit hidden vector space that can characterize certain objects. In this case, only 2 dimension is enough, which is the scale and rotation. So in order to do that, my methodology comes as this. We need to kind of characterize the regularity of some sort, and then we can do a normalization for downstream networks. So it will be kind of like an unsupervised attention mechanisms across different layers of neural network. So that is an unsupervised attention that is being defined right here. And in order to compute this normalization factor or the regularity, the problem itself is supposed to be intractable. So that is why that we compute this minimum description length as the normalized maximum likelihood. Basically, we believe that the optimal code length would be what is characterizing the attention of one brain region to another one. And you could also add in some specific saliency as a top-down attention as well. Maybe you want to focus on a specific property. You can also add into that as well. So basically, we have this regularity being computed as the optimal code length, and then it can be applied into any level of neural networks. So shown here, we tested it on recurrent neural net, convolutional neural net, gated neural net, and graph neural net, all kind of even the reinforcement learning version, and it has been killing basically in all kind of tasks, like computer vision, you have generative AI tasks, some question answering, and even some game playing and robotic control tasks. Yeah, so I would like to mention another thing about reward, which is that currently the reinforcement learning agents in the machine learning community, it tends to focusing on one stream of reward. Although there have been interest in DeepMind, I think in the past 3 years on distributed reinforcement learning, but this concept actually should be more binded towards the neuroscience and psychiatry, while the basic dopamine signaling actually process the positive and negative coding separately in different brain structures. And those reward errors or prediction errors and values, they are actually driving different important behaviors that characterize how human beings, like motivation, approach behavior, action selection. And we already know that different clinical conditions like Parkinson's, addictions, chronic pain, dementia, ADHD, they have their specific biases towards these reward processing mechanisms that is quite different. So this might be a very good entry point for us to build a spectrum of AI agents. So that is exactly what we did, because we are adopting an evolutionary psychiatry point of view, where the mental disorders can be considered as extreme points in a continuous spectrum of behaviors and traits during evolution. So they arise in some cases, like for instance, ADHD, although people have trouble living their daily life in many contexts, but also it might be very useful in the flight or fight scenario in surviving in the nature, right? And somewhat less extreme version of those can actually be beneficial in specific environment. So that is why that if we can model this, we can produce better AI algorithms. So we dive into some non-deep networks because we want to understand them first before moving on to more complicated ones. So one would be simply the multi-arm bandit. You could also have a context where people see something before makes decision. And also we have the full reinforcement learning problems where the action also changes the state, which the state actually reveals the reward. So we are changing them into a two-stream mechanisms where the reward of positive domain and negative domains are separated. And then the action selection process can be having a combined utility function of both things. So you can see that it can be applied to different levels of reinforcement learning agents, starting from bandit algorithms, some contextual bandit algorithms, some Q-learning or reinforcement learning algorithms. And then we could be either hand code or learn from data, the reward processing bias from neuropsychiatry literature. For instance, like Alzheimer's would be treating certain certain like reward interest have a diminished reward system, and addiction might have a heightened or sustained response. And ADHD would be more leaning towards how much memories you can see, or how much fast switching you are when you are learning, or when you are perceiving or learning from past rewards. So we see that this type of two-stream reinforcement learning outperforms all baselines in different type of either some tasks where we have human data, also like gambling tasks or other game playing. In this case, it's a Pac-Man game. And you can see that this is a highly non-stationary setting where we can flip the reward, we can scale the reward. And our type of algorithm is actually doing doing much better than others. And we can even replicate the same thing when our agent is not reinforcement learning, but just contextual bandit. We still see this benefit. And we can also see the hypothesis that certain conditions, like even dementia or ADHD, can be doing pretty well in some of the conditions. Although those are disclaimer, those are simply, we are just mentioning their names as a mimicry or emulator of the neuropsychiatric process below that. And we can see here are some of the interaction dynamics, and we can see some interesting behavior trait already, like the chronic pain agent, it doesn't care about the reward, but it only moves to avoid the stress. So it will also not die for a long time, but it's just not interested in pursuing the reward. While the addiction, it only is as much as possible, it's highly risky, the risk taking in this scenario. So a future line work would be, can we just based on this behavior trajectory, we can also do very early on diagnosis or prognosis for all kind of things. Yeah. And the third example is on language. I want to emphasize the importance of language because when we think about neuroscience, we think how it is distant from our interactions in daily life because we're not going to be wearing like an fMRI machine around our head, or even like an EEG can be sometimes intrusive for some individuals. But in the clinical setting, there are some data modalities that are very cheap and easy to collect, which is some transcription or features. And we want to showcase that those are already very important feature for us to understand what's going on in the cognitive basis. However, psychiatry itself is a very messy study, I would say, because there are many comorbidity between different clinical conditions, and DSM is basically a diagnostic manual which is changing like every few years. And many of the diagnosis still comes from self-reports where the patient has to fill out some questionnaires, and that questionnaires take place maybe like every few weeks or even months. So the temporal resolution is very poor, and there has also been calls about psychiatric research is in crisis because other medical fields all have some sort of quantitative biomarkers. People can just do a test and then follow along. But in psychiatry, sometimes if you go to a therapy session, you said that I feel depressed. And without any diagnosis or without any quantitative measurement, you will be already being prescribed with certain medicine. So in terms of that, psychiatry would be lacking some objective clinical tasks. And that is actually also, for us, AI scientists, a trouble because we want to understand in finer details. We want to get more information, more real-time feedback so that we can do better in the clinical setting. Yeah, so the National Institute of Mental Health, they actually suggested we can move from the diagnostic categories to functional domains. And I would also want to argue for utilizing cheap sensor data to capture this type of neuropsychological features. So one example would be working alliance. The working alliance is a therapeutic matrix, and that is very important because it is a predictor that is a predictor of the success of the entire therapeutic program. And this is therapy type agnostic, meaning that no matter if you have depression or schizophrenia or all kind of disease, and if you go to all kind of therapy, like cognitive behavior therapy, and even just psychotherapy, this indicator is very resilient towards across different therapies. So basically, it can be a very high predictive, a very good predictor. And also, it is very important in different levels of therapeutic treatment. It actually measures the alignment between the therapies and basically is a measurement of patient-doctor relationship, how they agree on their goals, their subtasks in the treatment program, and also how much their bonds are. And even in certain type of treatment, like if you have psychosis patient and you are doing cognitive behavior therapy and you ignore the therapeutic working alliance, this type of therapy can even be detrimental instead of helpful. So that is why that this type of cognitive quantities is very important. However, traditionally, you have to do this, which is another questionnaire, as many clinical instruments are. And the patient and doctor have to fill out this questionnaire every few sessions. And by the time of that, if you do not have insurance, you will be already spending thousands of dollars in this treatment. And maybe it just didn't click, right? So we would, and also you cannot really benefit from how powerful this type of cognitive features are. So I actually developed a cognitive inference framework where we go from the speech of the therapists and doctors, and you split them into, you diarize them into the patient and doctors, and you can compare the deep embeddings of the working alliance inventory with the working alliance inventory with what the patient and doctors are talking about, and that gives us some working alliance scales in the bond scale, task scale, and also the goal scales. And then we can have real-time turn level monitoring just during the session itself. And also we can have some clinical interpretation and downstream tasks built as well. Yeah, so by the way, so we tested this on the LX3 dataset. It is a counseling and psychotherapy dataset across 4 different clinical conditions. They're all well-trained therapists, and we don't have outcomes, so we cannot do other type of supervised learning upon them. But here is an example of such a transcript. So they're all anonymized, which is quite important. Yeah. So first thing we noticed that is that in our analytics, we can be averaging different type of sessions. Like the first rows are anxiety sessions by the patients and the therapist. We see that the patients and the therapists have some discrepancy in their working alliance. And it varies across different disorders, right? In the schizophrenia cases, we see more oscillatory behavior across the entire session. And we are seeing a monotonic increase in certain scales in the anxiety and depression sessions. We can even dive into the 3D trajectories. And here the 3D trajectory on the left is actually the bond scale, goal scale, and task scale of the working alliance. So basically, we can see that even from very early sessions, like 10 sentences in, you can already perhaps like diagnose these conditions into one condition, into one clinical condition versus the other, just based on how you talk with your doctors and how the doctors talks with you. And you can also have some interpretability by also comparing it in the topic space, topic modeling space. And here is some discrepancy, some variations between the working alliance average over all session or turns for different clinical conditions. And we can also do downstream dialogue classification, like I mentioned. Here is the binding with a BERT structure. And you could also have multiple cognitive properties. But in this case, we're also putting some personality scores over there. I know MDTI is not well respected in the academia, but still, so that is the part where we have the data set off, so we can also see whether our framework is useful in this case. So it is useful, and you can even come up with, if you are a patient in a certain personality type, how well we should be predicting your working alliance score be if you were meeting with another therapist of certain types. So here is another analytics. And I just want to point out that the dialogue, we can consider the dialogue as a landscape of this type of cognitive features like working alliance. And here is the hypothetical working alliance manifold in a dialogue space. Okay. By the way, the previous work has received a best paper award in one of the international workshop on health intelligence. Yeah. So basically, I feel like we are having this hypothetical working alliance manifold, and then we can map historical sessions and also real-time session into this trajectory. And then we can look at, why it's here having a very low working alliance score over there. And maybe there is a rupture event over there, and we can re-inspect at particular time points. We can know what happens in this therapeutic program. And we can even identify some breakthrough events and then learn from it. This will be very useful for training next generation clinicians because psychiatry is still in very high demand, and training a psychiatrist and therapist takes years and takes money. Yeah. And also, and with this manifold, we could even roll out treatment plans and basically to infer which treatment plan you should do in the next phase. So that is how we can use reinforcement learning to learn an optimal strategy. And now we have the reward, which is inferred here in real time when you are talking. However, this can be challenging, right? First challenge is that the therapeutic landscape is a dynamic maze, how you are interacting with the system. And also, you need to identify the patient's therapeutic state. We need to find the best strategy to reach the destiny. And also, these strategies are also anticipated, entangled with anticipated theory of minds of the patient, since now we're looking at both the patient and the doctors, how they're interacting. So with that being said, we actually build a recommendation system based on the idea how we can recommend the doctor to prescribe or actually recommend a topic to discuss in the next in order to maximize its working alliance. So the entire framework has different processing units. It has topic modeling to give you the labels of what the actions are. And we also have historical data set of characterized by reward signal, which are actually the working alliance scores. And this working alliance score can also be different scales. So if you are in, say anxiety, if you are an anxiety patient and you want to work on the bonds between the patient and doctor, you should train a specialized policy just by that. And then you could visualize this policy, which I'm not showing in this plot. We can also deploy those different agents into downstream tasks to even have sparse human feedback to correct for this type of AI agent or AI therapist, psychotherapy AI companions. Here's an example of, say, basically you are training inventory that you really care about, and their weighting score, like you can do some diarization, and it will be having real-time annotation of how well you are speaking at each round, and then lastly, you are predicting next action you should take. Okay, so I'm going to talk about the last study over here. It is a recent study. We did this qualitative work on proposing this concept of healthy AI. We know people are working on ethical AI, responsible AI, trustworthy AI, and also different elements to define how safety in AI is. But we would like to bring concept from healthcare towards understanding this type of large language models. Because by saying healthy, I'm not saying that we care about the well-being of this AI agent because they technically don't have well-beings. But also the doctors are not there to cure your well-beings, right? The doctors are there to cure your symptoms. Since some of the treatments, some of the symptoms are disruptive to you and disruptive to the equilibrium you have with your surrounding, with your family and friends. So in terms of that, we're not saying that certain mental agents, certain AI agents can have mental disorders, but we're just saying that they could be exemplifying some sort of symptoms that can be disruptive to their environment. So adopting a doctor-like approach, we're simply treating their symptoms, and then hopefully you can get back to your life and interact with your surrounding in a better way. In this case, AI can, after treatment, interact with their users in more healthy way. Yeah. So basically, the entire framework looks like this. We have an AI chatbot. We also have an AI user, which is not required. So this is just for training purposes. But we also have AI therapists. So these therapists can also be a human therapist. They are doing psychotherapy to these AI agents. So through the talking, you're offering it more context, since current day GPT-4 level model, it doesn't have experience or long-term memory yet, but we could be talking through things so that you can adjust these communication disorders. Sometimes the agent can be manipulative or gaslighting, as shown in many news right now. So perhaps talking it through over different options, as if it has some disruptive behavior, toxic behavior, might be a very interesting thing. You can also have AI critic to evaluate the entire thing if you want to train it in a reinforcement learning framework as on the right. So basically, the reinforcement learning based LLM can actually decide the context, whether I am ready to interact with the user or maybe I need to go to therapy, right? I have seen a lot of things, maybe I want to do therapy to brush up my skills. And then the chat history can also go to the critic, and the critic can have some reward, which actually corrects the entire system end to end. Yeah, so here's an example. The AI user enters the chat room, and then the chatbot thinks, maybe I should go to the therapy because I'm not satisfied with my response. And then the chatbot is talking with the therapist on the right, and then they exit the therapy because the human moderator is asking whether you have finished your therapy sessions or not, and then you can correct his answer. It turns out that it is actually doing better in terms of through the AI critics. We see that the AI critics believe that after the therapy, you have the manipulative level, gaslighting level, and narcissist level is pretty much 0. But before that, it is pretty high. Of course, this is entirely we cannot replicate it in benchmarks since all this AI agent they actually change every day, and big tech company they have their filters and stuff. Yeah. Okay. So I want to summarize this work by saying that I want to build towards a neuroscience-inspired AI framework where, for instance, we have on the one part, we have some highly predictive power model, which is some neural network model, and it is test-driven, but also it can be pinpointing to some neural correlates with some brain representations. And then it can also have some cognitive correlates as well for interpretable insights. So in terms of the digital health, if we consider the healthcare, what is challenging is that we now have 3 partners, right? So not only the agent, but also the doctor with patient. And sometimes when we are working with the AI, maybe we are focusing more on the human-computer interaction part. Sometimes the human-human interaction part is also very challenging. And also by having all those cycles of AI agents in different levels, we can also potentially share weights for different contexts so that it can not only do some more passive ways, like some real-time automatic annotation, or more interventional ways like the patient and chatbot, and also in a more offline way, like the educational training for next generation clinicians, and also has AI companion to basically help with the decision-making of the therapist itself. Yeah, so by doing that, we could have some more neuroscience-aware intelligent interface. So before our neuroscience inspiration, we would already have different sensor data and some decision-making data, right? And also some interface. But now we can have built method that I have built upon to compare different neural data, or by neural data, again, I mean the full spectrum, different levels of neural data with what we already get from the AI, and then we can correct it, and we can utilize the biological and cognitive priors to help us better build those models. So one example of such AI interaction paradigm is that we could be considering having safer extended reality with full simulation. So consider this: if you have like an extended and virtual reality realm where the user can enter and explore their own minds and using advanced AI and neural interface to dive into their thoughts, emotions, and memories. And then we would want them to be safe and controlled so that they can confront and overcome their deepest fear, phobias, or traumas. And also maybe we can unlock their full potential and emotional intelligence. And ultimate goal would be it can actually change how we understand and treat mental disorders. So basically, we want to, based on our understanding of the nervous system. So how does that connect to our overarching goal of digital twins, right? So because building this is not very challenging, but the challenging part is that how to make it safe and ethical. Since you could be having this type of interface to, say, for instance, for PTSD, there has been a lot of therapeutic treatment for VR therapies, or for someone who has a phobia for spider, you don't want to create a spider which is more and more scary, even powered by an AI, which can get out of hand and turns into like a Black Mirror episode. So instead of doing that, if we have the digital twins of how this individual is actually thinking through its process, how much it can handle a specific emotional stimulation, then we can basically do this entire scene simulation virtually before we even deploy the AI setup towards these various users. So it can actually speed up our benchmark of new interface very fast. Yeah, and also this is important for creating a reality, because realities is not just about visual input or haptic feedback. It has to do with different brain regions and different components of how our mind machine is completed of, like the cognitive element, the perception elements, the motor feedbacks, and even the emotions is very important, because our personal experience will shape how we are doing decision-making or perception in reality construction. And also the language is also very important, because the language unit of your brain also translate between different modality of information. And it can be the bridges between different brains or other people's realities. If we can model all relevant process, we can graph the program into any level of interface. For instance, even in intracranial XR or all those kind. Yeah, so I would like to end my lecture by imagining this society of digital brains. Say, in the next 30 years or so, we'll be imagining a world where each individual have a digital twin that can simulate every thought, interaction, and reaction to different treatments. And in this world, maybe we'll be living with a society with virtual humans and actual humans and AI agents, and collaborating and discussing with one another seamlessly, as if they are your friends or companion or people you know from work. And this can be very potentially very useful, because you could be digitizing human life if they pass away and all this type. And even you can also predict and prevent mental and physical health issues and enhance human performance in various domains. And of course, this envisioning is also plagued with ethical issues and data privacy issues, because we don't want to have our digital twins to be getting to the wrong hand. And also, who should have access to this technology? So all those things should be think about, because I feel like this will be an inevitable future that we'll be looking at in the future. So for my field of research, I would like to complete all the digital threads I presented here of the mind machine. So I want to replicate the entire process, manufacturing process of a brain, starting from even the gene aspect, the synapses, neurons, and all the way towards the society, because this is considering this constructionism understanding is very useful for us to build AI algorithm that is like more human-like and really understand. So it will be as bad as the human beings can be, right? And it can also connect to, like, this is kind of like brains in many jars. It is neuroscience, sometimes like to say a brain or jar or petri dish. How can we build those mind machines from ground up? We can also have dedicated think tank or banks of these brains and distribute brain system across individuals and have some sort of intracranial broadcasting or all those kind. Yeah. So basically, that is my hope to basically complete this entire field of research. And I want to offer a perspective, thanks to Todd's pointer. Basically, through all the things, we can actually answer these questions on our future AI. Can the AI really care about you? What do they mean by they care about you? And also, can AI actually live a life as someone else? Are they digital beings with a life itself? And can AI experience things? And also, can AI appreciate arts and music? This is quite important, because we know AI has been very good at generating those artists and creativity, but can we also appreciate them themselves? So those are very deeply baked in our histories and experience, the past experience, and also your personalities. And also, can AI have relationship and have friends and family? So by the end of the day, I feel like the goal would not to make an AI that is as smart as possible, but we want to make them as mind machine, which are also flawed as a human being, having their personality, where we as human beings can expect what to expect to when we are dealing with someone as a human or as a human like AI. Okay, so here is the conclusion slide, which basically mentioned most of the things. Neuroscience can help us build next generation AI. It is not only effective, but also better explain human behavior. And healthcare research can place AI model onto expressive spectrum and provide us with better ethical and safety constraint to generative AI. And ultimate goal would be to create a full spectrum of digital twins of our minds, such that we can build them from ground up and also be suitable to be binding with other interaction interface. And this predictive and personalized mind machine can also serve as a valuable addition to our society and help us create safer interaction, experiencing immersive realities. In 50 years, we will be looking into a hybrid society with those different things and the different levels of human beings. And new people have neural interface implants, can also compute anything, communicate with one another with their actual brains at home, or even host them in the public services. Yeah, so that is the end of my talk. Thank you for everything, and I'm open to questions.
Yeah. Thank you for this remarkable tour, Baihan. We have time for questions for sure. Maybe I'll start with one. Do I need the mic? We're going to pass the mic around just to people online. You covered a lot of work and a lot of ideas that resonated at very different levels. Your digital twin for the mind, great idea, but it's much more than a deep fake, which we can kind of do now, right? Digital twin of the mind, if I'm going to have it try out treatments for me or to try it on me, it's got to know my inner self. And that's never easy to get at. How would you train or put together such a thing? I mean, you showed your Pac-Man pathologies where you had your, ADD Pac-Man, your schizophrenic Pac-Man, they had different behavior. That's very coarse. That's not me, right?
Yeah.
I don't know what we were talking more at dinner about how you put that together, but how would you put together a digital twin of a human such that it would be useful for one of these things?
Yeah, thank you so much for the question, John. I feel like that also touches on the priorities, right? So we have this full spectrum, and where should we work on first, and how do we make them imminently useful for our society? So instead of like having AI algorithm ready for a technology that comes in 30 years. So I feel like it actually depends on like which level that you want to work with. If you want to focus on mental health issue, I would be imagining even the Pac-Man version is super useful from the diagnostic point of view, but also it is missing components which are more therapeutic, right? So that is why the second research is tackling more from the therapeutic point of view. It is not about, it is not even about your inner cognitive properties, but also how you interact with another human being, this interaction as an intermediate consciousness that is created through this language communication, right? So I feel like depending on like where we should be doing all those things. So one short-term thing would definitely be like the virtual reality example, since we have virtual reality interface everywhere. It is very useful, but there is a short-term challenge in that, which is that how can we make them safe and probable? So in that sense, maybe we will start from modeling the perception system, since that is where most of the reality of human beings or embodiments are coming from. But there could be other neuroscience principles that we could build upon. I also feel like maybe from like a long-term point of view, another overarching architecture that could be useful across all the level would be how say people are considering their different concepts as different contexts, right? So that is how we can build a human-like AI, which is really general, which is really a generalist towards different questions. We don't want it to be just good at creating a reality, but maybe we also want it to be doing speech recognition or appreciating art. So how do we do that would be, can we have some sort of concepts or modularities baked into the neural architecture? So a new level of neural networks that I'm currently is ongoing work is to create based off attractor networks, that is ancient concepts in theoretical neuroscience. But but instead of either mathematically defining it or just learning a recurrent neural net and have them automatically emerge, we have some regularizers to constrain them to form different type of attractors. And in my preliminary studies, this is very useful because it is in parallel towards what the traditional learning rules are, like backpropagation, even by using rules like contrastive Hebbian learning type of local learning algorithm. Without label data, we could be learning those neurodynamics in very precise ways, just with a very crude recurrent network with these local learning rules. So basically, that is a promising way. If we building different hierarchy of different brain regions, you can consider those attractor would be those concepts or contexts or intermediate thoughts that you are currently arriving. So we are characterizing not just the we're capturing not just the modularity in the networks, but also your mental states. So basically, that is how I view the like from a generalist point of view. It can be so that is work that I'm not presented here. It can be adapted to any neural network architecture that we currently have as a boosted way of having like an unsupervised learning type of methodology that can give you more constrained representation of mental states. So maybe that could be useful for across different levels. I'm not sure of particular problems yet. Maybe maybe in a mental health domain, some mental state can be characterized out, and we can build better treatment plans and also case summaries for clinicians or other type. But the opportunities is infinite. Yeah. Thanks.
Great.
Thank you so much. I have like 5 questions. I'll just do 2 for now. In the section on the working line between the therapist and the patient, I think I really appreciate where you're emphasizing how that relationship matters. Like you said, the human to human and the AI. And I'm thinking, just in a very practical way, have you or would you propose to test this idea, for example, if you say like propose a certain direction of treatment to achieve a certain working lines, would you try to test that on human subjects? And so what would be the process to do that in an ethical way? It'd be an ethical.
Yeah.
That's the first question. The second one, you can just answer together. You made a statement which is very interesting for all of us as humans, is that doctors, I think maybe in a Western context, don't always try to actually make you healthy. They try to help you address your symptoms so the symptoms don't impede your daily life, which I think is fits some of our experiences. I think as a Western version or like a particular post-Renaissance version of medicine, I wonder, there are other philosophies of medicine, maybe also from China, for example, or Eastern medicine. There are some philosophies of medicine that actually try to take a holistic view of the human in our mind, our soul, our emotions, and try to actually achieve health. If you took an Eastern or other philosophy, non-Western philosophy of health, and redid your thoughts, is there a version that could also have an AI interested in your actual health or the actual health of the AI, not just based on genetic health? So maybe one simple question, one question you don't have to fully answer.
Thank you so much, Daniel. I found them super fascinating. I want to first answer the first one. Actually, yes. So I'm already not only tested on the data set. I'm currently working with collaborators, amazing collaborator from Mount Sinai School of Medicine. So they actually have a group therapy setting, which is even more interesting, where they have group and family settings where for adolescent who has high risk for psychosis later on. So because psychosis actually happens in developmental stage as a very vital developmental stage. So basically, they have group therapy session for the adolescents who are talking with each other and the doctor, and also an actor, which is very important to do role plays to teach them about cognitive behavior therapy. And also, we also have another group, which is with their parents, very parents of this group of individuals. So I have analyzed this data set and find very intriguing trajectories on for instance, the relationship between the children itself, with children with the doctors is actually quite relevant towards the parents with their doctors, right? So that actually emphasizes the importance of families and how those things are. And also here is very interesting because in some activities, we have some psychotherapy type, but there are also role play where the actor is treating as a patient, and the parents are supposed to be the parents for this fake patient, and then other parents are critic critiquing this parent's behavior. So in a sense, as those conversations, the parents' role are swifted, where the parents, which is doing the role play, is now as a therapist role, and the other parents are now as a supervisor, which is a higher level of therapist role, which we find interesting dynamic as well. So I'm now waiting until their IRB approval to actually launch for the next stage, where it's that next batch of cohort of students, hopefully, because I have all the interface and demo system ready. So basically it'd be nice for them to run it in real time, right? So that they can see whether they want to take the suggestions of my system or not. And through the correction, maybe we can even make our system even better. Okay, I want to answer the second question. Second question is, okay, give me a moment because I'm trying to remember. Oh, okay. It is about, yes, the Western version of the health. Yeah, so basically, I fully agree with you that the Western version of the health is might be sometimes more focusing on treating the treatment. There are also other philosophy like holistic medicine or some Eastern medicine that focusing on well-being of the system, which could be very useful. But it is not at the current stage of our language model, since they don't have like a well-being or personality yet. But hopefully, once my model even evolved into that stage to have their own, so basically again their ability to gain these mental disorders, then that will be very useful because we can focusing also on their well-being. Yeah, thank you, Daniel. Hi, Patty.
So I find your vision to be very ambitious and powerful, but also very scary. And I'm not a philosopher nor a religious person, but it makes me sort of very uncomfortable because you're basically saying people can be modeled like machines. If we have enough data now, we can just model people and predict what their behavior is going to be. And so I'm very worried, not just about privacy issues, but in general, sort of, so that means we don't have free will. We're so predictable, like that a machine can just model us and be used instead of us. Also, will these predictions start being used instead of reality? It reminds me of the Minority Report movie where they predict that somebody is going to commit a crime before they commit a crime, and so they get put in jail before they even commit a crime or even think about the crime potentially. So I'm just, it's at the same time exciting, but also I think very scary, and there's just so much potential for abuse that it makes me nervous. Yeah.
No answer.
Okay. Okay. I thought there are some follow-up surprise. Yeah. Yeah. So I fully agree with you. Indeed, it is very scary to actually think about. I feel like what we can do is actually better prepare for it, because I feel like it is the inevitability of this type of technology would eventually come one way or another. So it'd be nice for us to actually through this process to understand more in this context. For instance, maybe starting from not creating a full personality of yourself, but just mimicking a particular function that you are most interested in, right? Maybe someone is interested in companionship to get rid of his or her or their own solidarity. Now it's actually a very important question in many Asian countries as well, and also in developed country. So basically, I feel like we can go one step at a time. I feel like similar things are also. I feel like when we are considering all those, I feel like the similar impact maybe like our case it would be much more scarier. But when we are seeing those AI generated videos of actual human beings which are not saying the very thing itself, it's already scary, like deepfake and all those things. And of course, people have been finding algorithms to deal with all those things. The key problem would be how do we interpret those data, right? Like you mentioned, we maybe don't want to go too far to actually take accountability on those digital models, since what matters, the same person can make this different decision at every iterations. It is not like we will be perfectly modeling this deterministic process as if everyone have a fate or destiny. So I feel like humans are not perfect. So in a sense that we are not going to be building like a perfect model also to 100% mimic everything. But I would agree that in specific sectors, like in criminal justice or deciding whether someone should get loans or not, or healthcare, again, healthcare access, and all those things, this decision shouldn't be based directly upon those digital twins that literally, right? So those would be more important for us to create new interface, new ways to interact with people. So that's why that I like to shape it as if it is more ways for us to create new things. So it is not the end goal. The end goal is not to have a digital copy of myself, but it is kind of like you doing all the things, trying out different possibilities for you to get better, right? Yeah. Thank you, Patty.
Yeah, so I had a quick, my question is actually a bit the opposite of Patty's, which is, I appreciate you putting in that slide based on the discussion we had, which was to say that it's interesting to make simulations and copies, but the real interest is, these systems don't actually care about anything and they don't appreciate things. And I think from our conversation, you agreed that this was something important to strive for. But what I wanted to ask was, I don't know that I saw in the work that you presented a path to get there. So it didn't seem like the neuroscience or the healthcare or the different approaches would get us closer to this. So I'm just wondering if there's a totally different way of approaching these kind of issues, or if there's something I was missing.
Okay. Okay, first of all, thank you so much for the pointers. It has been super helpful. I feel like one thing that is quite interesting is that neuroscience actually is a very rich medium. So even the memory system itself has been making the entire AI field very flourish for over years. But I would agree that to achieve a whole lifelong learning, a lifelong experience, and to share with other people is a very challenging task, and it shouldn't be just considering a single agent point of view. So I have also been testing upon multi-agent setting, and I find their interactions to be super interesting and can have very interesting learned policies, unlike having a single agent learn through an environment. So that is why that I'm betting against a more collective intelligence point of view, where basically that can AI experiencing, maybe it doesn't matter itself is experiencing, but it is important that it has something to be sharing with other people. It has a shared resonance with another being with respect to the same experience that you have, right? And also that how can we appreciate different things? So basically, so we need to have a memory mechanisms from what people have known, and also learn from developmental psychology and neuroscience on how brains are developed over time, how brains are collecting resources, and I already see this type of work very intriguing in very abstract space, like even the curricular learning aspect in the machine learning. It is trying to feed data in different sequence, and it will be having an entirely different trajectory. And I would be thinking the same way that now with finer details of how human beings are actually learning all those models. One example would be, I think 2 years ago, a group in Stanford, Dan Yaming's group, they tested different type. They're the guys who tested different type of neural network model and how to explain a certain, say, visual perception representation, right? So they find that if you have even like some contrastive learning type of way on some supervised thing, if you learn from ImageNet and all those kind, it is not doing as well. But there is a huge data set collected also by Stanford University. They have it's basically what the babies are looking at for the first 2 years of their lives. This is all first perspective view of videos and all this kind. And learning from that with self-supervised learning, the algorithm itself, even without training in the ImageNet, can already be highly predictive of how our human brains are processing in their benchmark. So in terms of here, maybe we don't see it, doesn't mean that they cannot, right? So it has to be many time steps, and this time step is pretty challenging. The other time step is sometimes even more challenging in the development or evolutionary scales how do we even model them? And there, but there are some solutions that we can look into, such as you can curricular learning or all type of evolutionary algorithm, or like a network perspective of how people are interacting. And I feel like one interesting thing is that brilliant idea. Now I think I also chat with some professors today earlier about I chat with Joe about it. Why some GPT-4 or all this type model are facing a roadblock where they cannot be getting smarter other than that. So what would be a solution beyond that, right? I believe one solution would be technically to have a diverse team or group of this type of AI model. And as a group that they come up with solutions, which is much more interesting. And that is where their own individual solutions cannot gain. So that is similar to we want to strive for more diversity and inclusiveness, to have perspective from different unique perspective. People have different lifestyles and anything. And then we have a very strong team together to solve for the most challenging problem. That would be also another way. Here, maybe someone, if someone lands a faculty position, for instance, in a certain university, maybe he or she or they cannot do the same way as if they are in a different environment because of the interaction he or she or they have with other collaborators and all those kind. Yeah. Thank you, Todd.
Hey, thanks for a tremendously stimulating talk. I'm reminded, sitting many hours with Marvin Minsky, who always wanted to download his brain into a machine. I have kind of a quantitative question for you, which is, if you think about kind of the human brain, you've got 10 to the 11, 10 to the 12 neurons, 10 to the 3 connections. You've got something on the order of 10 to the 15 weights there. Steve Wolfram recently, he's kind of well known for documenting every single character that he's ever typed on a keyboard. It's a few million words or so. So he trained an LLM based on everything that he's ever written. And what he was interested in was, could that kind of faithfully replicate him? Would it kind of ring true? And the answer came back that it really doesn't. Meaning it might type and kind of come across as his voice, but from an idea standpoint, not really. And so the question is, if you're trying to kind of model 10 to the 15 weights, but the only input into the machine is, the few million words that we have typed, there's kind of a mismatch there. And so this is kind of the Joe's question is there really enough input to actually capture a person? A person is the kids that they've hugged when they've come home, the emotional feelings, the music that they've heard. There's a tremendous amount there that only some of which is expressed by the keys that we type or the things that a computer could kind of suck up and hope to mimic as a digital twin. Just want to get your thought on that quantitative question.
Thank you so much. I feel like it is indeed the case. So I will summarize the challenge into 2 points. So one is that if we consider our brain as a huge neural net, which it technically is, it is a very over-parameterized paradigm, right? So even if you can't, what Stephen Wolfram has been writing for the entire life, it's not going to be enough to train a model that is replicating his thought process or all those kind. And the second one would be upon the second question is about.
Just a question about how close a digital twin
quantitatively
could you get to?
Yeah.
Given the amount of output of a person in digital form.
Yeah.
So much of a brain that's in digital form that you can capture.
Okay. For this part, I would like to first answer by pinpointing how people in say manufacturing or aerospace engineering, they will be thinking when they first come up with the digital twins. So their models, they are also pretty challenging because many times you cannot model all the components and you're measuring very indirectly on anything. For instance, you cannot rip open a $1 billion space shuttle just to look into a certain component. So your measurement will be very indirect, similarly to healthcare problem. So obviously just having the speech or text maybe is not enough to characterize everything. But still, I feel like one interesting thing that I still find is intelligence really characterized by the same individual's behavior or digital traces on the world, or is this intelligence characterized by communication? How this say maybe Stephen Wolfram's idea or brilliance is characterized on how he is interacting with his fellow researchers, friends, and all those type. And all those discussion is where his ideas come from. And even communicating all those things is what matters. So it's not just himself doing all those things. So similarly, maybe the digital twins here we are characterizing is a intermediate step, like the working alliance, right? It is not an element by itself. It's not just for this patient. It's a pair, it's a duo of this patient with these doctors. And that happens to be a very critical cognitive features for the interaction between these two. So similarly, maybe what we are characterizing is not just this AI digital twin for yourself, but we are characterizing is our interaction with these AI specific models. Maybe what matters more is how you interact with the model over time. Is this model more compatible to yourself? And is this model more understanding what you need at the exact moment or other type, right? So this could be another perspective in thinking all those questions. But for the first question, over-parameter iteration is also an issue in deep neural network model, and people have been coming up with theoretical proofs for how this type of model can also characterize some generalization properties and all those type. And if we have some regularizers, like say some sparsity or modularity, perhaps we can basically squeeze those over-parameterization better, as I was just proposing in the attractor network version, right? So that will be another way to think about this. But also, maybe these digital beings, they are not just they're beings by themselves. What matters more is the memory you have together, right? Maybe it's the goal. This is a very cliche thing. Maybe the treasure is not the treasure itself. The treasure is the memory we have together, right? Yes, things like that. Yeah.
Hi.
Hi.
I'm following up on Danielle's question on when you talked about, if I understood right, because I'm trying to make sure I get an understanding of it, about the trying to treating medicine as it is now, of treating the symptoms and trying to do things that are sort of building on what currently is the case. I worry about taking that type of approach. My own work is in the area of learning and education and how we can support better learning for children. And what really worries me in that context with AI is that if you just take the way education is done today, it's not something I feel good about. And I worry that as AI is being applied to it, it will further entrench what I see as bad approaches, and will make it further entrenched and more difficult to make the important changes that I think are necessary. It seems to me there might be an analogy in medicine that you could just be further entrenching what might not be the best way of doing things. So I would just be careful about just, if I'm understanding right, or just saying, well, that's what we can do now, so we should be doing it. It seems to me to step back and think, what is it that we think what are our values of what we want to do, and then see how we can use AI to support those values as opposed to doing the way things are now.
Thank you for the remark. I fully agree with you, because indeed, like even our AI model right now, like Google search, it actually filters out things. It doesn't necessarily fully powered by the large language model per se, but still it actually tells us, what is the world that is there, or the world we want to see, right? So which approach is better? Which search results is more genuine, right? So do we want to utilize this opportunity of using AI to correct for what is unfair, what is inequitable in the past of practices, some practices, where perhaps, so this would be a very good opportunity to indeed to actually do that. And with respect to the specific, the healthcare treatment for the AI, I feel like it is, indeed, it is not necessarily the best approach, since, maybe treating a patient is a holistic process by many culture. But on the other hand, the treating a patient itself is super hard, especially in mental health, because say if someone is depressed because he or she or they don't have a job, going to therapy will not change that depression per se. It can only change the way that you can deal with this depressed process, and then how it cannot affect your life around it even more so. But it cannot get you a job, right? It is not it's not gonna treat the problem that is happening inside your life. So that is why that I feel like this very restricted definition of a treatment happens to be matching with what the current stage of the AI model, where they can exemplify harmful behaviors, but technically speaking, they also don't have a well-being or consciousness or caring about other people. So basically, we are fitting with what exactly the definition of the current Western medicine has become. And I want to point out one interesting perspective when I chat with one of my collaborators, is that we have Turing tests, right? We have Turing tests for someone, whether it is AI or a human being. But maybe there's also Turing tests for some psychiatric disorder or something like that. We're not saying that, if I cannot distinguish this person's or this whatever agent's communication styles as a certain way, whether it's AI or a patient, from the Turing's perspective, from Turing test perspective, they are treated as the same. But we're not saying that this agent is a psychiatric patient, right? Technically speaking, they don't have well-being, so they will not, and they don't have this type of mechanism, so they will not exemplify that type of format. But from the same point of view, doctors are like, Western medicines are more like this type of, Western psychiatry are more like this type of Turing test level, where you have this symptom. That is where DSM-5 tells you that this is a psychosis, this is a schizophrenia, and it is entirely not quantitative at all, right? So maybe it is correct that as we progress the field, I was also hoping that my model can also lead the revolution towards merging more towards computational psychiatries, because that is a new emerging method over the last 10 years on more data-driven perspective to understand how those things are, instead of like just through the talking through 2 sentences, I diagnose you towards certain labels or conditions that you currently have. So maybe that this type of model can actually also help with, basically also help with dealing with the thing that is suboptimal at the current phase, like the psychiatry, right? Thank you.
Thanks, Mitch. I think that may be the last word. Let's all thank Baihan for being here. It's actually wonderful to be in this theater again with Baihan, kind of doing his version of Marvin Minsky's Society of Mind in many ways. So it kind of comes full circle for us. Thanks for such a provocative talk. We really enjoyed talking with you. So thank you very much.
Thank you, everyone. Thank you. And thank you, everyone online.